Welcome to today's webinar, Organism Making and Modding. I'm Nico Cavello, Product Marketing Associate of Next Generation Sequencing Services at GeneWiz, and I'm very pleased to introduce today's presenter, Dr. Michael Farrow. Dr. Farrow is a California-based scientist and entrepreneur who is best known for his work on the fundamental physics of the electroweak interaction at MIT and Stanford, human genome microarrays at Stanford, and synthetic biology at Teselagen. After leaving physics to spend several years developing software companies, Dr. Farrow's expanding interest in fundamental biology culminated in collaboration with Pat Brown and David Botstein to build and manufacture the world's first human genome microarrays at Stanford. Dr. Farrow then turned to systems biology with Lucy Shapiro and Harley McAdams at Stanford, where he developed an automated high-content diffraction limited microscopic screen of triply fluorescently tagged bacteria to better understand the bacterial cell cycle. In the aftermath of the Deepwater Horizon accident, Dr. Farrow and two Stanford colleagues started Teselagen as a way to accelerate synthetic biology and the bio-based economy. Seeing a big deficiency in biologists' ability to create what they imagine, Teselagen focused on making the mind-to-molecule process easier and faster with automated design, build, test, and learn software. Since then, Teselagen has had a laser-like focus on building professional state-of-the-art intelligent software systems for industrial-scale synthetic biology. If you have any questions for Dr. Farrow during the webinar, please enter them into the Q&A section and we will address as many as possible. And now, please welcome Dr. Michael Farrow.
Thanks, Nico, for that nice introduction. My name is Mike Farrow. I'm the CEO and founder of Teselagen Biotechnology. We're a software company here in San Francisco, and we have a sharp focus on enterprise software for synthetic biology. It's very much a privilege to be able to speak to folks during GeneWiz Week. I'd like to tell you a little bit about our R&D efforts and what we're trying to do to make the bio-based economy happen. So at Teselagen, we're building the information technology backbone for synthetic biology. We're accelerating genetic engineering with the world's only commercially available computer-aided DNA design, build, and edit platform. And it constitutes a secure, scalable platform for DNA building and editing. Our motivation comes not in small part from the Deepwater Horizon accident. The company was started about a year later. I think there are probably fairly reasonable alternatives to sourcing a lot of the stuff we use every day, from medicines to fuels to agricultural products, rather than from a barrel of crude oil, but from bio-based alternatives. So taking sun, air, water, and soil, using plants and microbes to produce those very same chemicals that we use every day in our as fuel for our cars, as petrochemical substitutes for feedstocks, for everything from flavors to fragrances, and then of course pharmaceuticals as well. So microbes can be thought of as little chemical factories. You can persuade them by re-engineering their genomes to make just about any biomolecule. In this case, adipic acid, which is a precursor molecule for nylon 6,6. This is a prominent industrial chemical. There's enough of this stuff made every year to fill a chemical tanker, car, train that stretches from Las Vegas to Los Angeles. So we're not talking about small amounts of commodities here. These are actually industrial scale products. Our origins are from the Joint Bioenergy Institute, in particular the Fuel Synthesis Division, synthetic biology group. And we have an effort to streamline their product development for creating alternative sources for ethanols, and specific cellulosic-based ethanols. But the inspiration for what we do comes from the computer-aided design world. So we take our cues from mechanical engineering, where you have sort of very clean workflows that take you from specifying a mechanical parts you might want to build to actually having it built and delivered, all in sort of a automated fashion. As far as the actual structure of the software goes, it looks a little bit more like electronic design automation, which is sort of the the equivalent for electrical engineering for automating the design, build, and test process. And the software actually has a lot of the characteristics of what they call EDA software. So our working hypothesis in starting the company was, what if we give bioengineers the same power over their design build environment that electrical and mechanical engineers enjoy? And that led us to a software suite that's still being constructed, but I'll give you sort of, an update about where we are in the R&D that we're working on right now. So it looks a little bit like EDA software, but more like a whiteboard that a biologist, a molecular biologist might use to sketch out a piece of DNA, not only 5' to 3', but also combinatorially. So you could have many choices of, say, a promoter or a ribosome binding site or a coding sequence. And then a lot of the, the stuff that goes around that are things you need to source your DNA, to talk to the automation systems, for security, for checking against business rules and biological rules, all kinds of things like that. We have a piece of intellectual property, so sort of the core intellectual kernel, I call it, for the software is a patent for the J5 algorithm, which comes from the Joint Bioenergy Institute, and serves as the sort of magic cookbook aspect of the software. You tell the software what you want to build, and the software will tell you how to build it. Not only can it generate a protocol in a sort of human readable form, but it can also generate a protocol in a machine readable form. So the methods we exploit for doing DNA assembly or for optimizing across various methods are the so-called, well, one class of methods are what we call the flanking homology methods. And these are probably better known for by the names of the actual protocols, like the Gibson protocol, CPEC, SLICE, yeast. But they all follow a very similar topological pattern, which we incorporate into the software. So, regardless of the particular protocol that you might be using, we can still, tune the instructions to follow that protocol. You can kind of think of it like if you really did have a magic cookbook, you might have a piece that's static. Say you had a recipe for 4 people, lasagna for 4, and you needed to make it lasagna for 400 with 20% gluten-free. Well, part of that recipe is going to be static, or the change isn't going to, there isn't going to be a change like preheat oven to 350 degrees, but part of it's going to be dynamic. So what the algorithm does is sort of recalculate the dynamic parts of that have to change. The static parts, can stay the same. So that's what we can do when when people ask us to do a particular protocol. We can just sort of tune it for the particular protocol at hand and change that part dynamically. The other major class, I would call it topological class, because it's kind of the way the DNA is fastened together. There's so-called type 2 endonuclease methods, and the sort of leading protocol in that class of methods is the so-called Golden Gate protocol. FX cloning is another one. MoClo falls into this category as well. So there's a whole host of protocols that fall into this topological class. Another method that we're looking at closely that actually we can probably hammer into one of these classes, although we may want to build some specialty software for adapting to it, is the user method, sequential user cloning of multiple inserts. And this particular method is of interest for reasons that become clear if you're trying to do certain types of DNA assembly. So we're taking a very close look at to see if we can incorporate it into our software. And then of course the ligase cycling reaction, if you're doing assembly from de novo synthesis. This is a fairly straightforward approach that allows you to simply create single-stranded DNA bridging oligos and then link them together by ligation, via ligation. So the application spaces are all of the sectors of biotechnology that use DNA at the core. So industrial enzymes and microbes for medicines. Amgen is a significant customer of ours. For basically they're an antibody company now. They modify antibodies. And then we have a fairly intimate relationship with Dow Corporation through their Dow AgriSciences division. And they're pretty intense users of DNA, in particular what they call gene stacks. So they had to make fairly long constructs in using hierarchical methods. So I'll go a little bit more into detail about our relationship with Dow AgriSciences and what we're doing for them. So sort of the paradigm that we used when we started the company was this synthetic evolution paradigm that said I may have a design phase where I incorporate modeling and simulation. But at some point it's got to get real. I got to make something and try it out. So that would be the build stage. And then you have to test it, of course, see if it worked. And then based on those tests, you would learn something and adapt to that. And then you could go directly back to the build stage and test again, or you might take it right back to the design and try again from the design point of view. But we believe this can be fairly automated now because of the way we can modify protocols on the fly as we learn about the success or failure of the constructs. We can actually think about making this almost continuous loop until you converge very quickly on the optimal design. So this is something we took to the National Science Foundation in cooperation with our colleagues at the Joint Bioenergy Institute, and we managed to get this funded at the SBIR level, and we turned that sort of vague concept into a concrete workflow that we knew we had employed ourselves at the Joint Bioenergy Institute as well as Stanford. And then we took that concrete workflow and turned it into a set of software modules. And the modules kind of follow the workflow to some extent, but they're somewhat autonomous from one another, so you can use them in isolation as well. So it kind of starts up at the upper left, this diagram, and then kind of wiggles its way over to the right. You start kind of where you think you might want to start, which is with data. So you need to start with sequences. Sequences are in plasmids, plasmids are in strains. You kind of want to have all of that stuff at your fingertips. And then you want to have your interface with the molecules of interest. So that means being able to look at it from both DNA, protein, and pathway point of views. And then once you sort of sketched out what it is you want to build, you need that magic cookbook piece that says, okay, I've done my best at telling you what I want. Now you tell me how to make it. So once you know how to make it, both while you're designing it and then afterwards, you can do a little cost modeling and quoting to find out, sort of where can I source these materials. And then because this is so far it's all happening in a computer, you can send stuff directly to automation, and that's kind of the magic. The software can generate both a human readable version of the protocol as well as a machine readable version of the protocol. Once the stuff is made, of course, you'll want to test it, both from a quality assurance point of view, as well as a functional point of view. And all of that information can then go into a decision analytics and modeling module, which closes the loop for you. All of this has to be sort of undergirded by some sort of workflow management because, there's a lot of balls in the air here. So the benefits for, a Fortune 50 company like Dow are many. I think probably the one that most academic researchers don't realize, and probably we didn't realize it either until we really engaged with Dow, is the issue of security. So protecting their valuable intellectual property is very important. So they really want systems that are under their control. They're not necessarily just going to go use some vendor, interface here, a vendor interface there. They need all of their information very centralized and under lock and key, so to speak. And then they go sort of poke out to various vendors when they need this or that in order to do what they do. Scalable, they want it to be used across not only campuses across the United States, but around the world. It has to be fast. The whole point of this thing is to reduce time to market. It's something we learned also moving from academia to industry, is that time to market is everything. Of course, you have to be safe and compliant, and we incorporated a lot of stuff under the covers, which actually checks for business rules to make sure you're obeying not only the sort of internal business rules, but also regulatory rules that may come from government agencies. And then flexible, we had to build it in a modular way because people may want to deploy different modules at different stages. But ultimately, that sort of central paradigm is important too, which is to automate this whole mind-to-molecule process. So you can think of a very simple workflow example that incorporates DNA at its core, where I have a user, a customer, interacting with an interface, creating a design which can then get sent to construction automation and then sequencing for quality assurance. Success or failure comes back into a knowledge base and goes back to the user. Physical DNA goes into a physical repository. The nice thing about saving physical DNA is you can use it again very cheaply. So I'd like to shift gears a little bit and talk about a case study or about our relationship with Dow AgroSciences. We sort of broke the work with Dow into 3 phases because there was a lot of stuff that they had a need to do, and we're through phase 1. It was a pretty nice success. We were able to clear upstream bottlenecks for them in this case, and also increase their target hit rate from, well, I can't tell the exact numbers, but it was an order of magnitude. So it was pretty impressive, and it's encouraged them to then now go to phase 2 and phase 3 with us. And what we learned in that engagement is that biotechnology is really an information technology, and that modern professional information technology is an important element of the success. So even with companies that have a core expertise in a computational element, what we find is they still don't want to burn a lot of their resources on doing this more nuts and bolts type stuff. So that was a valuable finding for us. The other thing that we found is that I think the next big gains will be made by integrating with service providers like GeneWiz, because we can't really smooth out this mind-to-molecule design, build, test process without very quick, fast links to service providers so they can quote you, get you the material on a short time scale, allow you to test it, also maybe do QA for you, stuff like that. So let me just go into a little bit about our approach with Dow. They're like I mentioned, they're making very big gene stacks. So if you think of a piece of DNA as being sort of just a string, and you might think, okay, all I need to do is sort of partition it in half, and then in half again, and then half again, until I get to some little oligos I can synthesize, and then I'll, do various techniques to reassemble that back into the construct. And yes, that does work. But what we found is the world is quite heterogeneous, and people are doing all kinds of crazy stuff. And sometimes they think in functional units, sometimes they think in just raw blocks of DNA. So we're taking the approach that we want to accommodate any user's sort of strategy for doing DNA assembly. So we've taken this sort of operator-operand approach. So the operand is the string or fragment of DNA, and the operator is the thing that joins those 2 strands together. And you can partition the DNA into operands depending on your strategy. It may be a functional one, it may be just optimized for synthesis. But eventually you get to these atomic elements which you either have synthesized or you might just PCR them up out of stuff you have in the freezer. And then the question is, how do you put it back together? And so that's what our software does. It basically automates that process for you. And at the sort of, again, at the atomic level, you may have combinatorics involved. So you may say, well, you know, for gene number 2, I actually want 10 variants of that. So you have the combination of both combinatorial elements and hierarchical elements built in. The other piece that's we found with working with Dow that's very important to them is that it's nice to have all this stuff, you know, stuffing your pipeline, but if your laboratory information management isn't really ready to handle it, you're going to get a bottleneck immediately downstream. So we're writing a new workflow management system for Dow. They were very unhappy with existing sort of laboratory information management systems. We're doing this kind of high throughput synthetic biology. So we're building a sort of state-of-the-art workflow management system that uses kind of a stateless chain of methods that take data, and then a method is really just a task, and then spit out some data, and they could be chained together into sort of infinite series of steps. So this sort of loosely coupled stateless modular workflow allows Dow to have maximum flexibility for a whole variety of lab work and rework possibilities. This is just some screenshots about what the workflow manager looks like. There's workflow initiation and definition. There's the hierarchical design editor, where you're defining your operators and your operands. Material sourcing, this is really important. So as you're building the DNA, you can query the system to see if a particular vendor can supply it to you. That's completely under your control. We don't say use this vendor or that vendor. We're not a user interface for a vendor. Simply, we provide links to vendors that provide reagents, and it's your choice. If you check off the box that you use that, then we can optimize for that vendor. Inventory management is important. You got to know what you have and where it is in the pipeline. So this is just an example of some content tracking. Workflow builder. So you're allowed to build, you know, an arbitrary workflow through a little macro generator. You have a task library. You drag them up to the workflow. The workflow then gets executed, and you have, you know, status monitors that show you where you're at in your workflow and cool stuff like that. This is just the batching queuing interface. You have navigation, you have the status. Those little bubbles there are different team members that are assigned to a particular task that they're working on together. So you can quickly see, you know, who's involved with what part of any particular workflow. So this in particular is the interesting task for us today, which is the DNA assembly task. So DNA assembly instructions that are coming from the, you know, automatic protocol generator / magic cookbook get sent to the LIMS system, and in the LIMS system they can get converted to machine instructions. So the little pop-up here in this particular view is are the machine instructions for a lab site Echo, which is a pretty popular machine now for people doing DNA assembly. And then you have quality assurance as well. So this is also where it loops back in. If you have, say, a vendor like GeneWiz, which is doing your sequencing, you may want to grab that data back into the system and compare it to what you thought you were going to get, and just make sure that everything's, you know, copacetic. So you have a comparison of, you know, what I wanted to what I got type of thing. For the people who are a little bit, you know, into the software stuff, a little bit nerdier, this is our technology stack. So at the very bottom level, you have your database, and we optimize either for Oracle 12c, if you want to spend the money for that, or Postgres. The middleware kind of web web server is called Node.js. So it's all written in Java. We interact with the Node.js server using JavaScript. And then at the highest level, we use a system called React Redux, which is also all JavaScript. So it's sort of JavaScript front to back. And then it's all wrapped up into something called a Docker container. And this is what allows us to deploy either behind the user's firewall or up in the cloud if you want to be a AWS, Amazon Web Services, software as a service user. Either way, it doesn't matter. So this is kind of what that synthetic evolution bubbly diagram looks like now as we're going forward and kind of learned, what role we play in the world. You still have this design, build, test, adapt cycle, but service providers are extremely important in making this. Oops, sorry. At the build stage, we really want tight integrations with service providers. And again, this is something that's defined by the user. We don't get in the way of the relationship with your service provider. We just want to make it super easy and comfortable. And then again, at the test stage, we want to make it really easy for people to get their QA results and get that back into the system. Again, we're not building interfaces for service providers. This is sort of internal software for big companies like Fortune 50 companies like Dow that really need control over their processes, but really want good integrations with their service provider. Yeah, so that's kind of where we're at the moment. So thank you very much. Appreciate your time and attention, and I'll turn it back over to Nico for Q&A.
Thank you, Dr. Farrow. We greatly appreciate you taking the time today to do this webinar all the way from Singapore. We did have some good questions come in throughout the webinar, so let's get to the Q&A session. Question comes from the UK. What are some examples of how your industry users are utilizing the platform?
Thank you, Nico. That's a good question. So I had that little triangle picture there. We were kind of lucky to get, when we first started, one or more customers in each of these sort of major sectors. So Amgen was our first customer, and they're doing antibody modification. Then Genomatica, and they're basically modifying bugs to make chemicals. And then our biggest collaboration has been with Dow, and they're basically doing plant modification. Pesticide resistance, or insect resistance is their big deal. So yeah, those are the three major categories.
Thank you, Dr. Farrow. The second question is coming in from Florida. Is it possible to share my sequences with a collaborator, either inside or outside of my group? Also, can this be done without downloading the sequence?
Yeah, that's a good question too. So I can't really do a live download of the software on this webinar, but if you do go online and check it out, there's Google style sharing. We don't use Google Docs to do it, but we took our inspiration from Google Docs. So we basically replicated their logic for sharing sequences, and also things like rolling back sequences. If you make a mistake, you can always go back through your history, and so yeah, you can share it with people in kind of like a Google Drive actually type of interface. So yeah, that's what we did for that, and it works pretty well. People like it.
Thank you, Dr. Farrow. The third question is coming in from good old Boston. How well tested is your algorithm, the J5, for DNA assembly instruction generation? So can I rely on it to put together a complex library?
So yeah, so it's actually pretty reliable. It came out of the Joint Bioenergy Institute, actually Nathan Hilson's group, and it was used for a number of years there before we started commercializing it. And it's got thousands of man hours of testing behind it, because J5, the core algorithm, is used pretty heavily around the world. And then when we started engaging with Amgen, we just had a whole bunch of little edge cases that were particular to making antibodies. And then we had a whole bunch of edge cases when we worked with Genomatica, and then a whole bunch more. So it's had almost all the little funny kinks worked out of it. So yeah, it's pretty good. And our Zeta's using it now, and they've never had a failed construct. I mean, they do obviously reasonable QA on the output to make sure it looks reasonable, but they've never had a failed construct. So it's really nice because it makes everything very repeatable. You don't have to guess at anything.
Great, thank you. I believe we have one more question. It's coming in from Israel. Do you do pathway modeling and simulation?
No, we don't. So we kind of pick it up where you've decided you really want to make something badly. Now you need some help making it. We would like to work with people who do that. In fact, some folks here, that's one of the reasons I'm in Singapore. Some folks at National University of Singapore have some good modeling software. And then, of course, JV has some and stuff. But we just have focused on the sort of design build nexus for now. But we'd like to add stuff like the upstream modeling to make it, to get sort of more useful for people while they're actually thinking about what they want to put on the whiteboard.
Thank you, Mike. That's all we have for today's webinar. I would again like to thank Dr. Mike Farrow for being part of our GENIUS Week webinar series. There is a day and a half left of GENIUS Week, so make sure you check out the Lab Startup program, as well as the DNA Awards, the Credit Awards, and exclusive promotions. Our next webinar will be held today at 3 p.m. Eastern Standard Time, featuring Dr. Antonina Selkov, and she will be presenting on immunosequencing analysis and its clinical applications. Again, I'd like to thank everyone for coming out today to listen to Dr. Michael Farrow, and have a great day.
Thank you. Thanks, Nico.